All right, diving in today, we've got YOLOE, a paper that's making waves by really streamlining real-time object detection and segmentation.
Definitely a hot topic.
And the quick summary, YOLOE is a single, super efficient model.
Efficient.
That's hitting state-of-the-art zero-shot performance.
Wow.
And it works across the board. Prompt-free scenarios, text prompts, visual prompts, you name it, even better. It boasts improved transferability, cuts down on those training costs, and runs faster than YOLO World v2.
Faster is always good.
Plus, for all you hands-on folks out there, they've put the code and models up on GitHub. If you're serious about this stuff, go check it out.
Definitely worth a look, especially if you're building systems that need to make sense of visual data on the fly and do it quickly. Think of autonomous vehicles, right?
Yeah.
They need to spot unexpected objects in real time, or robots working in dynamic environments that need to follow instructions given in plain language. This kind of tech is fundamental to so much of what we're trying to achieve.
Yeah, exactly. Object detection and segmentation, those are the cornerstones. And for years, the YOLO family has been the go-to solution when speed is paramount. But traditionally, these models have had a bit of a limitation. They could only recognize a fixed set of objects they were trained on, which, let's face it, isn't how the real world works.
Yeah, the real world is full of surprises.
You constantly encounter things you haven't seen before. So you need a model that can detect, well, pretty much anything.
And that's where YOLOE gets really interesting. It tackles this head on. It aims to be this unified model that can take in all sorts of prompts, text descriptions, visual cues, or even no prompt at all, and then accurately and efficiently identify and segment any object you throw at it. In the past, attempts to build this kind of versatility often hit a wall. They were just too computationally expensive to be practical for real-time use cases.
Yeah, you're right. We saw the potential with architectures like DynoX, but the resource demands were just too high. And training separate models for each type of prompt, well, that's not very elegant or efficient, is it?
Not really.
So what YOLOE is going for is the best of both worlds.
Sounds great.
And that's what we're going to unpack today. Our mission is to delve into the nuts and bolts of how it achieves this real-time seeing anything capability. We're going to look at the key architectural innovations and really analyze its performance. This will give you, the listener, a clear understanding of why this paper is creating such a buzz.
It sounds like a plan.
So let's start with the basics, the YOLOE architecture. If you're already familiar with YOLO, you'll recognize some of the building blocks here.
It builds on that familiar YOLO foundation. You've got the backbone for feature extraction, then the PAN, the path aggregation network, which does a great job of combining feature maps from different layers. Think of it as giving the model the ability to see both the fine details and the broader context at the same time.
Oh, for sure.
And then, of course, you have separate heads for different tasks, regression for predicting bounding boxes, segmentation to generate those pixel-level masks, and object embedding.
Okay, and things start to get really interesting when we bring prompts into the picture. So let's say you give it a text description, like a red bicycle, or a visual cue, maybe a cropped picture of a cat. YOLOE takes that input and converts it into what they call normalized prompt embeddings.
Right.
And these embeddings essentially become the classification weights. They guide the model towards identifying the regions in the image that match that prompt.
That's how it zeroes in on what you're looking for.
And it does this by contrasting those prompt embeddings with the anchor point object embeddings that the model learns.
Exactly. It's all captured in equation 1 in the paper, which lays out their core formula, label equals O.pt.
Okay, break that down for me.
So O represents the object embeddings. PT stands for the prompt embeddings. And that dot product operation between them, that's what produces the label prediction. In simple terms, the more similar the object embedding and the prompt embedding are in this high-dimensional space, the more likely it is that that particular anchor point actually corresponds to the object being described by the prompt.
Makes sense. So let's dig deeper into how YOLOE tackles text prompts specifically. The researchers introduced a pretty clever mechanism they call Re-parameterizable Region-Text Alignment, or RepRTA.
Catchy name.
What's the problem they're trying to solve here?
The main hurdle when you're working with open set scenarios and text prompts is efficiently aligning that rich semantic information packed into the text with the visual features you've extracted from the image. And this gets particularly tricky when you're dealing with a potentially limitless number of object categories. Past methods often relied on these complex cross-modality fusion techniques to try to bridge that gap. But these fusion operations can be really computationally demanding, especially when you're using embeddings derived from large language models with huge vocabularies.
Yeah, that sounds like a bottleneck.
Big time.
So how does RepRTA offer a more streamlined and crucially more efficient solution?
What RepRTA does is introduce a lightweight auxiliary network. This network takes pre-trained textual embeddings, and these are usually obtained from a CLAP text encoder. The important bit here is that these embeddings are cached before the main training of YOLOE even starts. This auxiliary network then refines these embeddings specifically for better visual semantic alignment, and all of this happens during the training process.
Okay, so I get the alignment part. But what about the parameterizable bit? What's the magic there?
This is where it gets super elegant from an engineering standpoint. Once the training is done, the parameters of this auxiliary network are merged right into the object embedding head of the main YOLOE model. The paper details this with equation 3, which shows you how those new kernel parameters, k prime, are derived. It combines the original kernel kt with the output of the auxiliary network as it works on the prompt embedding. The really brilliant part. This means your inference architecture ends up being identical to a standard YOLO model.
So no added complexity at runtime.
Exactly. Zero added computational overhead during inference. It's like you get all the benefits of a more sophisticated alignment process during training without paying the price in terms of speed at runtime. And that's absolutely huge for real-time applications.
I can see why they're excited about this. So you're basically baking those improved text-vision relationships into the model without sacrificing speed later on. And because the textual embeddings are pre-computed and the auxiliary network is so lean, the training cost stays manageable, right?
You got it. It's a really efficient way to bridge that semantic gap between text descriptions and what the model actually sees, even when you have a vast vocabulary.
Okay, let's switch gears a bit. What happens when your prompt isn't a text description but a visual cue? How does YOLOE handle that?
For visual prompts, they've come up with something called the Semantic-Activated Visual Prompt Encoder, or SAVPE.
Another great name.
The challenge here is that a lot of existing visual prompt encoders are built on these heavy transformer architectures. Some even use deformable attention mechanisms.
Deformable attention.
Yeah, it lets the model focus on relevant parts of the image more flexibly than standard attention, but it's more computationally expensive. And then there are those that rely on additional vision encoders. This creates a real headache for deployment and efficiency, especially on devices with limited resources.
So SAVPE takes a lighter approach.
Much lighter. It's got a streamlined design with two separate branches that work together. First, you have the Semantic Branch. This one focuses on extracting those general prompt-agnostic semantic features from the multi-scale feature maps that come out of the pan. It uses regular convolutional operations, so it's not adding a lot of computational overhead.
Okay, and what about the second branch, the activation branch? What does that do?
The activation branch is where the visual prompt itself comes in, usually represented as a mask or a bounding box. It also takes in the image features, and its job is to generate these grouped, prompt-aware weights in a low-dimensional space. These weights basically highlight the parts of the semantic features that are most relevant to that specific visual prompt.
So it's focusing the model's attention.
Exactly.
And how do these two branches come together to create that final prompt embedding from the visual input?
The final prompt embedding is calculated by combining the outputs from those two branches, and the paper lays this out in equation 4. The semantic branch gives you the overall visual context, while the activation branch uses the specific visual prompt to fine-tune those features. This makes them much more targeted. The result is a super efficient way to process visual cues that's way less complex than those transformer-based methods.
It's like a more direct and computationally friendly approach. Now, YOLOE also needs to be able to handle situations where there isn't any explicit prompt given at all. How does it manage to detect anything in a completely open-ended scenario?
That's where the lazy region prompt contrast, or LRPC, comes in. Traditionally, to do prompt-free object detection, people often use large language models.
Right.
They generate category names for whatever they detected. But the paper points out that this adds a ton of computational overhead because, well, these language models are massive and complex.
I can imagine. So LRPC tackles the problem in a more efficient way.
It does. Instead of trying to come up with category names on the fly, LRPC reframes it as a retrieval task.
Oh, interesting.
It uses a special all-objects prompt embedding. This embedding is trained to pick out the anchor points in the image that are most likely to contain any object at all. You can see this illustrated in equation 5. It shows you how a subset of these promising anchor points, O', are selected. It's all based on a threshold, delta, applied to the similarity between the object embeddings and this universal prompt embedding, EPPES.
Okay, I'm following. And where does the lazy part come in?
The lazy part is that they only compare those pre-selected anchor points against a built-in, super extensive vocabulary of category names. The ones the model thinks actually have an object in them. This way, you avoid those really expensive similarity comparisons for every single anchor point across the entire image. Huge efficiency boost. They mention in the paper that they've assembled a vocabulary of 4,585 categories.
Wow, that's quite a library.
So you've got this huge pool of potential object names ready to be retrieved.
And that means that at runtime, in a prompt-free setting, there's no need to crank up a big language model just to figure out what you're looking at.
Nope, you've completely sidestepped that computational bottleneck. And that results in much better efficiency and overall performance for that prompt-free scenario.
That makes a lot of sense. Now let's talk about the nitty-gritty of training. What datasets did they use to get YOLOE to be so versatile?
The core training relied on two main datasets, Objects 365 and GoldE. Interestingly, they specifically left out images from the COSIO dataset during this pre-training phase. The idea was to focus on learning those more general, open vocabulary representations.
So no bias from a more specialized dataset.
Exactly. Now, to get the segmentation masks needed for training, they used a clever trick. They leveraged the Segment Anything model, or SAM 2.1, to automatically create pseudo-instance masks based on the ground truth bounding boxes that were already in those datasets. And then these generated masks went through some filtering and simplification to reduce noise. For training with those visual prompts, they directly use the ground truth bounding boxes as their cues. And to train that special all objects prompt embedding for the prompt-free task, they just reuse those same datasets, but they treated all the objects as belonging to a single generic object category.
It's kind of bootstrapping the segmentation training data.
Very much so.
And the paper highlights a significant reduction in training time compared to YOLO World. Can you give us some concrete examples?
Absolutely. Take YOLOE V8S. They trained it in just 12 hours.
12 hours.
Using a cluster of 8 NVIDIA RTX 4090 GPUs. Now compare that to YOLO World, which under similar conditions took around 41.7 hours to train.
That's a big difference.
And the larger YOLOE models showed similar time savings. They had a training process that started with a focus on text prompts for 30 epochs. Then they did a very short 2-epoch fine-tuning specifically for SAVPE with those visual prompts, which really helped keep the overall training costs down. Finally, they trained that specialized all objects prompt embedding for just a single epoch. So yeah, massive time savings for researchers and practitioners who want to work with these models.
Makes the technology much more accessible. Now, what about the specific training objectives? What loss functions were they using?
They mostly stuck with the proven methods used in object detection. Binary cross-entropy loss for the classification task, a combo of IOU loss, that's intersection over union, and distributed focal loss to fine-tune those bounding box regressions, and then binary cross-entropy loss again for the segmentation task. All pretty standard stuff for YOLOE. That distributed focal loss is particularly useful for tackling class imbalance, which is a common issue in these object detection datasets where some object categories appear way more frequently than others.
Right, it helps to even things out.
Exactly.
And to see how well YOLOE could generalize to new, unseen data, they did transfer learning experiments on the COSIO object detection dataset.
Yep, COSIO is a classic benchmark with a fixed set of categories. They wanted to see how well the model could transfer its knowledge. So they tested two common fine-tuning strategies. Linear probing, where you only train the last classification layer and keep most of the pre-trained weights frozen, and full tuning, where you update all the network parameters based on the COSIO data. They carefully controlled the number of training epochs for each approach as well. Linear probing only used 10 epochs, while full tuning used anywhere from 80 to 160, depending on the size of the YOLOE model.
Okay, let's dive into the results. The paper makes some bold claims about YOLOE's zero-shot performance on the LVIS dataset, especially when compared to YOLO World v2. What are the key takeaways?
The results, which are neatly laid out in Figure 1 and Table 1, are impressive. Take YOLOE V8S, for example. It achieved a significant boost, 3.5 points higher in average precision, or AP, compared to YOLO World V2S in a zero-shot scenario on LVIS. And what's really important for practical applications is that this improvement in accuracy also came with significant speedups at inference time. It was 1.4 times faster on an NVIDIA T4 GPU and 1.3 times faster on an iPhone 12.
Wow, so both more accurate and faster.
And they also showed better performance on those rare object categories in LVIS, which are usually a real pain point for open vocabulary models. This suggests that YOLOE has a better understanding of a wider range of visual concepts.
That's a big step forward in both accuracy and efficiency, which is exactly what you need in real-world scenarios. How did it fare against other models that are specifically designed for certain types of prompts, like T-Rex2, which focuses on visual prompts, and Generate-U, which is built for prompt-free detection?
When they compared it to T-Rex2, which, as you said, is all about those visual prompts, YOLOE VAL actually did better. Yeah, it showed a 3.3-point improvement in APR, which measures recall, while using less training data and having fewer parameters overall. Against Generate-U, in that challenging prompt-free setting, YOLOE was either on par or even outperformed it, with a slight increase of 0.4 points in AP. And all of this while using a model that was 6.3 times smaller in terms of parameters and significantly faster.
Impressive. And what about segmentation? How did YOLOE handle that in a zero-shot setting on LVIS?
The segmentation results detailed in Table 2 were encouraging too. YOLOE showed strong zero-shot performance for APM, which stands for Average Precision for Mask. It even beat some versions of YOLO World V2 that had been specifically fine-tuned on LVIS data for segmentation. This really highlights how well YOLOE's learned representations generalize.
It can adapt to new tasks without needing that extra training. Now, the paper mentions a slight dip in APF, which measures performance on the more common object categories. Any ideas why that might be?
It seems that the small decrease in APF might be a side effect of combining object detection and instance segmentation into a single model, as they suggest in the Oblation Studies summarized in Table 5. This multitask learning approach sometimes leads to trade-offs, where optimizing for one task might have a small impact on another. But the gains in overall AP, and especially on those rarer categories, seem to more than make up for this slight reduction.
It's a worthwhile trade-off. To really validate YOLOE's capabilities, the researchers also looked at how well the knowledge learned during its pre-training could be applied to the standard COCO object detection task. What did those results tell us?
Those transfer learning experiments on COCO, which you can see in Table 4, showed that YOLOE is really good at transferring its knowledge, even with just linear probing, where they only train those final classification layers for a very short time, just 10 epochs. YOLOE achieved a good chunk of the performance you'd get from a model trained from scratch on COCO. And when they did full fine-tuning, where all the model's weights were allowed to adjust to the COCO data, they saw even more substantial gains in AP. Importantly, they got these high levels of performance on COCO with way less training time overall compared to training a similar YOLOE 8 model from scratch on COCO.
So pre-training on that more diverse open vocabulary data set not only helps with those zero-shot tasks, but it also lays a strong foundation for learning more specific closed-set tasks in a really efficient way.
You got it.
The paper also includes a bunch of Oblation studies to really understand how YOLOE works and what impact each design choice has. What were some of the most interesting findings from those experiments?
The Oblation studies are super insightful. Table 5, which they've cleverly titled Roadmap to YOLOE, systematically breaks down how each design decision contributes. They found that simply reducing the initial training epochs compared to YOLO World V2 already had an effect. Adding a global negative dictionary during training also helped. And removing that computationally expensive cross-modal fusion layer sped things up considerably, although it initially hurt accuracy a bit. But they managed to recover and even surpass that lost performance by incorporating that more powerful mobile CLEP encoder and then refining it further with the RepRTA strategy. And finally, as we talked about earlier, adding the segmentation head led to a slight trade-off on those frequent categories.
Right. And what did they learn about the Semantic-Activated Visual Prompt Encoder, or SAVPE?
Table 6 is all about SAVPE. They found that it significantly outperformed a simpler approach, which was just pooling semantic features based on that visual prompt mask. This really highlights the importance of that dedicated activation branch within SAVPE. It effectively learns to figure out which parts of the prompted visual region are more semantically important. They also experimented with different numbers of groups in the activation branch and found that using 16 groups struck a good balance between performance and efficiency.
Okay, and last but not least, what about the lazy region prompt contrast, LRPC, in that prompt-free setting?
Table 7 and the visualization in Figure 5 really demonstrate how effective LRPC is. By only doing those computationally heavy category retrievals for a small, carefully chosen set of anchor points, the ones most likely to have an object, they achieved really impressive speedups with just a tiny drop in overall performance compared to the naive approach of checking every single anchor point against the entire vocabulary. Figure 5 really brings us home visually. It shows that dramatic reduction in the number of anchor points that need to be processed. It highlights how redundant those initial dense predictions are and how efficient their filtering mechanism is, which is based on that similarity threshold delta.
It's like they're cutting out all the unnecessary work. Besides the hard numbers, the paper also includes some really nice visualizations of YOLOE in action across different prompting scenarios. What do those qualitative results show?
The visualization analysis, starting with Figure 4 and continuing through Figures 6 to 9, provides really strong visual evidence of how versatile YOLOE is. They show how it can do accurate zero-shot detection and segmentation on all sorts of new objects from the LVIS dataset. It can handle all kinds of customized text prompts, from broad descriptions to really specific ones. It can use different types of visual prompts, bounding boxes, single points, even free-form shapes, sometimes spanning across multiple images. And it can identify a wide variety of objects even without any prompt at all. These visualizations really drive home the practical capabilities of YOLOE and how well it can handle real-world scenarios.
It's really impressive to see it in action. So to wrap things up, what are the core innovations and benefits that our technically minded listeners should take away from our discussion about YOLOE?
The biggest breakthroughs here are YOLOE's efficiency and its unified architecture. It gracefully handles a wide range of open prompts, making it capable of real-time seeing anything. That Re-parameterizable Region-Text Alignment, or RepRTA, is a brilliant way to achieve strong alignment between text and vision without adding any computational burden during inference.
Yeah, that's really clever.
Then you've got the Semantic-Activated Visual Prompt Encoder, or SAVPE,
Catchy.
which is a lightweight but very effective way to encode visual prompts. And the Lazy Region Prompt Contrast, LRPC, offers a highly efficient method for identifying objects when you don't have any explicit prompt.
So a lot of innovative techniques coming together, and these innovations translate into real advantages over existing methods.
Absolutely. Compared to models like YOLO World V2, T-Rex 2, and GeneraU, YOLOE offers significant improvements in both performance and efficiency. You get lower training costs and much faster inference speeds, making it a far more practical choice for real-world use, especially on devices with limited resources.
It's a big step forward.
Yeah.
Now, taking a broader view, what impact do you think this work will have? How might YOLOE shape the future of research and applications in computer vision?
I think YOLOE is a significant step towards truly versatile and efficient vision models. Its ability to seamlessly integrate different types of prompts within a single architecture, coupled with its real-time performance, makes it a very solid base for future research on open prompt-driven vision tasks. It could lead to breakthroughs in areas like human-computer interaction, where you want more intuitive ways to communicate with machines using natural language and visual cues. It could also lead to more adaptable and robust robots and more efficient and general-purpose perception systems for autonomous vehicles.
It's exciting to think about the possibilities. It really makes you wonder about the potential of these efficient and flexible seeing anything models. To our listeners, I encourage you to think about what this could mean for your own work. Whether you're in robotics, developing perception systems, exploring new frontiers in human-computer interaction, or even working in fields we haven't touched on today, how might YOLOE inspire new applications or research directions? To dive deeper into the technical details, I highly recommend checking out the code and pre-trained models, which are all available on GitHub. Thanks for joining us for this deep dive into YOLOE. We'll see you next time.